Units of measurement. Units are important, okay? Units are a big deal to me. So there's two systems of units that are common. Most of the world uses the metric system. Here in the United States, we have to be difficult, and we are clinging onto the English system. And I hope in this class, if you have not already become convinced, I hope to show you that the metric system is really a much better system. You just need to get to know it, and it's so much easier. So scientists officially use the International System of Units, which is based on the metric system. And it's called the SI system because in French, you put the system before the international, and so SI units. I didn't take French in high school. I took Spanish, which has turned out to be much more useful because I can actually say the Hispanic names. So that's been awesome. I went to high school in Iowa. When I went to high school in Iowa, I think the population was like 97% white. I mean, you talk about vanilla, oh my goodness, right? And so Spanish was this really exotic language, and it just seemed kind of frivolous to take Spanish. And then I moved to California. I'm like, hey, I at least have a clue. I am not fluent in Spanish, but I have a little clue, and I can pronounce names. So yay, 3 years of high school Spanish. Anyway, I don't know where French, yes, anyway. There is a difference between the SI system and the metric system. The differences are minimal and I think completely inconsequential. So we're not going to care about the differences. So these are our base units for the SI system. Length, the main unit is meter, mass, kilogram. For chemistry, we use the gram more often. It's just a cousin of the kilogram. Time is in seconds. Hey, that's the same, right? Temperature is measured in kelvins. In chemistry, we also use Celsius a lot. Amount of substance is a mole. That's a very good chemical unit. And then electric current and luminous intensity, we don't deal with those in Chem 1A, so we'll ignore them. So a meter is a little longer than a yard. The rest of that's kind of interesting, but they've got it defined in a very particular way. I want you to know roughly what size a meter is. It's roughly the size of a yard. Because if you have a concept for how big these units are, then you can understand, is my answer crazy or not? I was just trying to FaceTime me. Okay, so that's measure of length or distance is the meter. Kilogram is a measure of mass. Now, mass is a little bit different than weight. Okay, weight is actually a unit of force. It's a measure of the gravitational pull on matter. And so what you weigh on the Earth and what you weigh on if you were to go to the moon would be different. If you took your bathroom scale, it would give a different reading. Okay? Anybody planning to leave the planet this semester? You are? Yeah. Okay. Can I go with you? So as long as we stay on the planet, we can use mass and weight interchangeably. But mass is actually the quantity of substance. Do you actually lose part of your body when you go to the moon? No. You're the same amount of matter. It's just that the moon is smaller than the Earth, and so it doesn't pull you toward it as much. So the weight changes, the mass doesn't. So mass is a matter of the quantity of substance. The common unit of mass that we use in chemistry is a gram. A nickel is about 5 grams, if that helps you get an idea. A gram is a small amount of stuff, okay? So a nickel is 5 cents, a nickel is 5 grams. A kilogram is a lot larger. It's about 2 pounds. So, if you're concerned about your weight, you may like to look at it in kilograms instead, because then it looks like you weigh half as much, but you don't actually. It's just a smaller number. time, I don't think we need to explain that. The second is the second. We do have a very specific definition for it, which I will not require you to know. Kelvin, we'll talk more about this as a unit when we talk about temperature. But temperature is a measure of the average amount of kinetic energy. So the warmer something is, the more the particles move, the higher the temperature. Temperature just measures that. Temperature also helps us to understand which direction thermal energy is going to flow. So something that is hot has more kinetic energy because the particles are moving faster. I tell people, think about barefoot people on the beach. Okay, I use this in Reedley. It works really well, but it probably doesn't work so much here. If you go to Reedley Beach, which, if you haven't heard of that, it's just this sandy place on the side of the Kings River. It sounds real fancy and everything, but it's just a lot of sand on the Kings River. But anyway, so think of maybe sand out in the parking lot. If you spread some sand on the ground today when it was like 105 or something, the sand's going to get really hot, right? And if you're walking barefoot on hot sand, are you just going to stroll along? No, you're probably going to hot foot it to the river, right? There's a reason they call it hot foot, because your feet are hot, so you step really fast. So warm things moving quickly. If you go to Pismo this time of year, why do we go to Pismo? Because it's cold and windy and overcast at the beach, right? People in Southern California don't understand. We just want to get away from the heat. We have seen too much sun. We don't really want to see the sun for a day. So we go to Pismo and the sand is cool. And you can just stroll along barefoot and it doesn't hurt your feet at all. Cooler temperature, slower movement. So we've got high energy at high temperature, and that high energy is going to flow to something with a colder temperature. So you think about hot water and ice cubes in it. Is the water going to get hotter and the ice cubes get colder? No. The energy is going to go from the hot water into the ice cubes, melting the ice cubes, and it'll end up all at the same temperature. Because nature tends to want to do that. It wants to just kind of equalize everything. So we get thermal energy transfer from the hot to the cold. So temperature is a measure of the average amount of kinetic energy something has, and it also helps us to understand what direction the energy is going to go. So here we come to the different temperature scales. The Fahrenheit scale is one that we use to tell us that it was 105 or whatever it was today. This is a typical English unit. Here we've got the freezing point of water at 32 degrees Fahrenheit and the boiling point at 212. How do they come up with these numbers? I kind of think maybe the guy made a thermometer and he put marks on it, and then he just, oh, well, that happens to boil at 212. And oh, look, it froze at 32. And they just went with it. I mean, it just seems that random to me. So that's not a metric unit. Metric units are based on powers of 10. So the Celsius temperature scale is a metric scale. And so it's sometimes called the centigrade. Centi is 1/100th. So we take the difference in temperature between freezing water and boiling water, and we divide it into 100 degrees. So water boils at 100 and it freezes at 0. Why are we so obsessed with the boiling point and freezing point of water? Because it's a temperature that's easy to make. If you've got ice and water mixed together, it's going to be 0 or close to it. If you've got boiling water, it's going to be very close to 100 degrees. Because a lot of this stuff, remember, was developed long before electricity was discovered. And so how do you obtain a particular temperature? They referenced everything to the boiling and freezing points of water, because everybody can get a hold of water. So that's the Celsius temperature scale. And then we also use the Kelvin temperature scale. And the difference between the Kelvin scale and the Celsius scale is that they're just offset. So here we've got 0 as the freezing point of water, and on the Kelvin scale, we have 0 as absolute 0, the theoretical lowest temperature that could ever exist. That's the temperature at which the motion of even the atoms in a substance stops. Everything completely still. They haven't quite gotten there. There's, of course, people that are like, oh, let's see if we can get to absolute zero. So they're spending who knows how much money. I think they've gotten to like 0.05 or something. They're getting real close, but nobody can get there.
Isn't it impossible?
It could be impossible. But if you tell a scientist that something's impossible, that just fuels their fire to do it. Oh, you said it's impossible. I'm going to prove you wrong, right? So, yeah, we like to do stuff like that. But you can't get lower than absolute zero. It's a theoretical lowest temperature. You definitely can't get lower. Whether you can get to zero is debatable, but some people believe you can. So if we look at these scales, the difference, 273 to 373, it's still 100 divisions. And so the unit Kelvin, and it's not a degree Kelvin, it's just a Kelvin, and the Celsius degree are the same size. The unit is the same size, but they're just offset. Zero is in a different place. We'll use kelvins a lot when we talk about gases. I kind of said that already. So these are the relationships, and these are equations that you need to memorize. People don't usually have problems with the Kelvin scale, Kelvin to Celsius. Sometimes we just do 273, but it's technically 273.15. So you just, take Celsius temperature and you add 273.15 and you get Kelvin. As long as you can remember the 273, if you do it wrong and you end up with a negative Kelvin temperature, try it the other way, because you can't get less than 0 Kelvin. And then this is the Celsius conversion. So you take the Fahrenheit minus 32. Make sure you finish that subtraction. There's potential for problems on your calculator here. Finish the subtraction and divide the whole thing by 1.8, and you'll get Celsius. So, an example. Mercury melts at 234 Kelvin, which is lower than any other pure metal. That's the story. What is its melting point in degrees Celsius and in degrees Fahrenheit? So here is our first word problem. Well, we've got a number here. The numbers are usually important. So pull that out. 234. So that's something we're given. And then the question, what is melting point in Celsius and Fahrenheit? So what do we need to do? We need to convert a unit. We need to convert that temperature in Kelvin to Celsius and to Fahrenheit. Was there an equation that had Kelvin and Fahrenheit in the same equation? No. We had Kelvin and Celsius, and we had Celsius and Fahrenheit. So maybe we should go to Celsius first, and then to Kelvin. So that's the Kelvin temperature. The equation that was there was Kelvin equals the temperature in Celsius plus 273.15. So we want to find this. We need to isolate it in the equation. We're going to do a lot of basic algebra, okay? Rearranging equations. And the thing about an equality like this is kind of like a teeter-totter. If you do something to one side, you have to do the same thing to the other side for it to still be balanced and equal. So this may be a little tedious for some of you, just humor me. So if we subtracted 273.15 from that side and subtracted 273.15 from this side, it would still be equal because we did the same thing to both. I mean, that looks like a strange thing. So then on the left, we have Kelvin minus 273.15 is equal to 273 minus 273 is 0. And so what we've done is we've isolated the Celsius temperature. So now I've got it over there on the left, but that's going to equal the Kelvin temperature, which was 234, minus 273.15. So then you get out your calculator. So negative 39.15. Is that what people were saying? Okay. And then that's going to have the unit of degrees Celsius. It's okay to have a negative degrees Celsius. You can't have negative kelvins. So calculators, you should always bring them. And I want you to work it with me and shout out the answer. I'm still going to punch it through on my calculator, and that gives everybody at least some time to do it. When you do things on your calculator, it's really easy to press buttons wrong. And so it's always good to do it twice. If you get the same answer, you're either making a very consistent mistake or you got it right. If you do it a second time and you get a different answer than you got the first time, then go for best 2 out of 3. Do it again. So what you'll find me doing is I'll punch it through on my calculator and then I'll ask you, and hopefully somebody else is doing it and we can agree that, yeah, I did it right, because I make a lot of mistakes. I'm human, and humans do that. Okay, so now, are we done with the problem? No, because it asks for 2 answers. And that's one of my pet peeves. You get questions that there's like 2 parts to the question, or they ask you for 2 things, and students do the first one and forget the second one. So watch out for that. I'll get you if I can. Now, could we take Celsius and convert it to Fahrenheit? Sure we could. And of course, I picked it so it would be difficult. So the equation was the Fahrenheit temperature minus 32 divided by 1.8. So we have to rearrange that again, right? I should have written it somewhere else. So there's no room. Let's see if I can do this. Oops, not like that. Ta-da! Oh, done. There it is. Okay. So we need to rearrange this. Some students like to put the number in and then rearrange it. I don't recommend that. One semester I thought, oh, we'll go with that. Oh, it was a disaster. It's much easier to arrange when you've got letters and simple numbers than when you get long, big, messy things. So we're going to rearrange this first. We want to separate degrees Fahrenheit. And then, if you're really good with algebra and this is boring you to tears, I'm sorry. We could get a box of Kleenex or something. But there are people that just need a review of this. Okay, so we've got divided by 1.8. Divided by 1.8, we want to do the opposite, and so we're going to multiply by 1.8. Because 1.8 divided by 1.8 is 1. And so these essentially cancel out. If we multiply one side, though, we have to multiply the other side. Okay? Now, I can do this. I'm going to get rid of that stuff because it's confusing. Now this should be relatively easy. To get rid of minus 32, we add 32. We're going to do the opposite. So we're going to add 32 to that side. And if we add 32 to that side, we have to add 32 to this side. Now, order of operations matters. Those 2 things get multiplied first and then added with the 32. And so these guys add up to 0, and we end up with Fahrenheit equal to the Celsius temperature times 1.8 plus 32. So now we can take that Celsius temperature that we calculated. Be careful with the minus sign, don't want to lose it. 39.15 times 1.8 plus 32. So that's still in my calculator. I'm just going to multiply by 1.8 equals plus 32 equals, and I get minus 38.47. And the unit would be degrees Fahrenheit. And we haven't officially learned about significant figures, so we're just going to go with that for now. Any questions? Is that a reasonable, both of those, are those reasonable temperatures? It says mercury melts at this temperature that's lower than other metals melt at. Minus 38 Fahrenheit, minus 39 degrees Celsius, those are low temperatures. If we came up with 5,000 or something, we would be alerted to the fact that we did something wrong. And sometimes it's something real simple that happens on your calculator. So you just have to watch out for that. But always looking at the answer and thinking about it. Is that possible? Does that make any sense? Sometimes you can't tell, but sometimes you can. If you're rusty on your scientific notation, see Appendix 1A in the textbook. We're going to use scientific notation. We don't cover that in this class. Oh, that reminds me. On Saturday, my husband is running what he's calling 1A boot camp. I'll get the times for you and tell you on Thursday. But basically, he's having this big group session on Saturday when most people are probably available so that you can brush up on some of the more basic things that I might be going through too fast for you. So I'm not talking about scientific notation. I'm going to assume that you've got that under control. Also on Mastering Chemistry, there is a math review assignment that's for practice. If you're a little rusty on your math, you might want to go through that and brush up on that. What's really nice about the metric system is based on factors of 10. And so to make different sized units, we just put a prefix in front that changes the size. Here are the multipliers. Some of these are a lot more important for chemistry than others. Kilo is very important. Centi, milli, micro, nano, and pico are pretty important. Mega is kind of important. Those are the most important ones for chemistry. So mega is a capital M, kilo is a lowercase k. Whenever we see this in front of a unit, it means that we're multiplying that unit by this factor, 10 to the third. Most of them are 10 to the multiple of 3. So we've got 3, 6, 9, 12, 15, 18. These two guys in the middle are weird. This is minus 1 and minus 2, and then the rest are minus 3, minus 6, 9, 12, 15, 18. But the multiplier is used to change the value of the unit. In the English system, we've got inches and feet and yards and miles. We need different units because you don't want to measure the distance from Reedley to Fresno in inches. It'd be a really, really big number. You want to measure it in miles. And so we always choose a unit that's more comparable to the size of the thing that we're measuring. A piece of paper. What do we measure paper in? Inches. 8.5 by 11 inches. We're not going to measure it in miles because the number would be really tiny. So in the metric system, we just use these prefixes and we can change the size of the units, and it's always by factors of 10. The prefixes are universal and can be used on any unit. How many inches in a foot? 12. How many feet in a mile? 5,280. How many yards in a mile? I can never remember that one. Random numbers, right? How many teaspoons in a tablespoon? 3. And there's 2 cups in a pint, and 2 pints in a quart, and 4 quarts in a gallon. Right? It's just like so completely random. So we don't have to memorize and remember all those different relationships, 16 ounces in a pound. It's all factors of 10. We learn the metric prefix and what it means, and then we can use it for all these different units. So it's really a neat thing. So kilometer. Kilo means 10 to the third. So 1 kilometer is 1,000 meters, or 10 to the third meters. Centi is 10 to the minus 2. So 1 centimeter equals 10 to the minus 2 meters. Now there's other ways that you can write that relationship. And if you've got a grasp of the metric system, you might say, well, I always do 100 centimeters equals 1 meter. Awesome, do that. I do that too. But what I find is when you mess around with things like that, people who have not turned on their common sense will end up saying that 100 meters is a centimeter. Well, if you don't have a good grasp of size of units, again, but that's like saying there's 5,280 miles in a foot. That's not right. If you follow this pattern, you'll never go wrong. 1 centimeter. The centi, the prefix goes on one side. What it means goes on the other side. 1 kilometer. What does kilo mean? It means 1,000. It means 10 to the third. Those are the same. So you just substitute in what the prefix means, and you've got your relationship. So those are the prefix multipliers. This is the decimal form, but who wants to count all those zeros? Personally, I think it's much easier to remember these and then deal with it with your calculator later. So let's do some examples. How long is 4.5 megameters in meters? Well, 4.5 megameters, what does mega mean? 10 to the 6th. So that's 4.5 times 10 to the 6th meters. It's a megameter. Mega's big. Oh, he makes mega bucks. He makes millions of bucks. Mega is a million. 7.13 times 10 to the minus 9 liters would be how many nanoliters? Well, 7.13 times 10 to the minus 9 liters. What does nano mean? 10 to the minus 9. Nano kind of sounds like 9, doesn't it? Nano is 10 to the minus 9. So instead of this 10 to the minus 9, we can put the prefix that means that. And so that's equal to 7.13 nanoliters. Now, obviously, I chose that example so that it worked out really well. But that's the idea. Any questions? The little letter in front of the unit, the metric prefix, has a mathematical meaning. It's just a power of 10. You need to memorize them. And then we can do all kinds of things without having to look at a chart or look anything up. So we've talked about base units, gram, liter, temperature, kelvins and degrees Celsius, seconds. Those are base units. We also have derived units. And derived units are derived from a combination of other units. And so volume and density are derived quantities that we encounter frequently in chemistry. So other examples are rates of speed, miles per hour or meters per second. Those are a combination of length and time. Volume is a measure of space. We can use length to measure space if we recognize that if we have a cube, let's see my sad excuse for a cube. So there's a cube and it's three-dimensional. And how do we measure the volume of a cube? Well, you've got a length and a width and a height. Length times width times height gives us the volume of a cube. What could we measure those lengths in? Oh, how about meters? So if those were in meters, length, that's a bad L. Length times width times height equals volume. If those were in meters, we'd have something meters times meters times meters. That's going to be meters cubed. Meters cubed means meter times meter 3 times. Meter, meter, meter. Okay? You can do that with any length unit. Throw the prefix in there. You can have cubic millimeters, cubic centimeters. You could have cubic megameters, cubic kilometers. It's a measure of volume. That unit is derived from a length unit by combining it with other length units. Common unit we use for volume in chemistry, because we don't deal with solid objects that are easy to measure very frequently. We deal with a lot of liquids. We use the liter and the milliliter, but those are related to these derived units of liters, of meters cubed. So if we look at the sky, here's a cube that's 10 centimeters on a side. So the volume of that would be 10 times 10 times 10, 1,000, right? 1,000 cubic what? Cubic centimeters. So the volume of that guy is 1,000 cubic centimeters. If we divided this cube into 1,000 little cubes, each little cube would be 1 centimeter on a side, right? So this little block here would have a volume of 1 cubic centimeter. This volume we call a liter. Why? Because some people decided to call it that. Why that particular volume? I don't know exactly. It seemed convenient at the time. Anyway, 1,000 cubic centimeters is equal to 1 liter. This guy is 1/1000th of the liter. What prefix means 10 to the minus 3? Milli. Okay, so just a little review on negative exponents. So 10 to the minus 3, minus means 1 over. So that's 1 over 10 to the third, or 1 over 1,000. 10 to the third is going to be a 1 with 3 zeros. That tells you how many zeros to put after the 1. So 1/1000th. So this cubic centimeter is also called 1 milliliter. A cubic centimeter and a milliliter are exactly the same volume, just by a different name. We usually use cubic centimeters when we're measuring solids, and we usually use liters and milliliters when we're measuring liquids. Just like you would measure the volume of gasoline using gallons instead of cubic inches or something. But you would measure manure for the garden in cubic yards and not in gallons. Here are some relationships between units. There's a couple of these I want you to know. I want you to know this one. 1 inch is exactly equal to 2.54 centimeters. Notice that it says exact. They actually redefined the inch to be exactly 2.54 centimeters. The rest of these you may have to oops, didn't mean to do that. The rest of these you might have to look at to figure out a problem in mastering chemistry or something. This one you should know. A liter is 1,000 milliliters, which is 1,000 cubic centimeters. And what's a lot easier to use is this guy right here. That is an overlooked conversion factor, because they'll give you something in liters, and then later you need meters or something, and you're like, whoa, there's no connection here. 1 cubic centimeter is equal to 1 milliliter. And just in case you're curious, that is also 1 cc. In the medical field, oh, give him 1 cc of this stat, right? So they say on the doctor shows. cc stands for cubic centimeter. It's just a different name for that same unit. So those two, basically, you need to memorize. The rest of them, if you need them on an exam, I'll give them to you. Density, also a derived unit. And this is something you need to know as well. Density equals mass divided by volume. What's a common unit for mass? Gram. What's the common unit for volume? Milliliters. So grams per milliliter, or grams per cubic centimeter. So for liquids, we tend to use this one. For solids, we tend to use this one. They're actually exactly the same, because a milliliter and a cubic centimeter are exactly the same. Density is a physical property. It's not a chemical property. It's a physical property. You can demonstrate the density of something without destroying it. Density does depend on temperature. The density of things changes a little bit with temperature. So you should be able to do density problems. So here's another word problem. A piece of galena, an ore of lead, has a volume of 4.6 cubic centimeters. If the density of galena is 7.5 grams per cubic centimeter, what is the mass of that piece of galena? So, they're throwing this story in here, and you're just like, that's a boring story. Well, yeah, maybe it is, but do we need all those words? No. Do we need to know that it's an ore of lead? No. Focus on the numbers. So we've got this number, and we've got this number. So see them, pull them out. So we've got 4.6 cubic centimeters, and we've got 7.5 grams per cubic centimeter. Writing the unit this way with a slash is a lot easier on a word processor or a computer. You don't have to get out the equation editor or do funky things with your spaces, which is just lame sauce. But when you write it with your own little hand, make it a vertical fraction. It is a fraction. Make it look like a fraction. Okay? So 7.5 grams over cubic centimeters. Now, what are these things? It helps to understand what these units measure. What does cubic centimeters measure? A volume. Okay, it also says volume of, so that should be a clue. So that's the volume. And density is, so this is the density. Okay, what are they asking for? Mass. Is there an equation we can use? Sure. Density equals mass divided by volume. So we need to rearrange the equation and get mass by itself, and then we'll be good. Be careful, okay? If it's been a while since you've done algebra, review and do some practice on it, because what happens is people do dumb things. They understand the chemistry and all the other stuff, and they do something really stupid with algebra, and they get the wrong answer. It's just tragic, really. So we're going to rearrange this or multiply by volume on both sides. Because then we have volume divided by volume. Those cancel out. So the mass is equal to the volume times the density. So we've got the volume is 4.6 cubic centimeters, and the density is 7.5 grams over cubic centimeters. Units act like variables in algebra. That they'll cancel out or they'll multiply. You know, we did centimeters times centimeters times centimeters with centimeters cubed. That happens with units. Here we've got centimeters cubed in the numerator and centimeters cubed in the denominator. Anything divided by itself is 1. We say those cancel out. So what we have left is 4.6 times 7.5 is equal to 34.5, and the unit that's left is gram. And that's good because gram is a unit of mass, and we're trying to find the mass. If you do something and you end up with cubic centimeters, you went wrong somewhere, right? Or if you end up with grams per centimeters to the 6th power or something, right? Something went wrong. So this is an example of showing your work. If you have any issues with algebra, I would really encourage you to write the whole thing out. It may seem tedious, but getting the wrong answer and then having to go back and do it again is more tedious. Not passing the class and having to take it again, that's like the epitome of tedious, right? So just take the few extra seconds to write it down, write it all out, show what you're doing, pretend someone 100 years from now is just going to be fascinated with your chemistry homework, right? I need to write everything out so they can see exactly what I did. I need to document this. So this part, write that out if you have any issues with algebra. Some of you can look at that equation and write down the rearranged form. Awesome. Do it. But write down the rearranged form. Put the numbers in with the units. A unit is very important. Okay? There was a space, what was it? The Mars Explorer, they sent a spaceship basically to Mars. And it was supposed to orbit Mars and send back all this awesome information. You know, sending anything into space, millions of dollars. Well, lots of people working on this. Some guys were using inches, some guys were using centimeters. They didn't make it clear to each other that we were using different units. So they calculated things incorrectly, and it was orbiting at the wrong distance from the planet, and it couldn't maintain that orbit, and so, crash, gone. Seriously. Yeah, burned up. You know, as something goes into the atmosphere of a planet, it burns up, gone. Over units. How dumb. But gave us a great thing to throw at students. You know, don't be dumb like the NASA scientists, right? That is rocket science. But write the units out. Because if you rearrange this equation incorrectly, the units will show you that because they won't cancel out the right way. Units are your friends, okay? So there we go. There's the mass. So what I would say for showing your work, minimum is what's in the box here. Every number that has a unit has its unit every single time you write it down. A little bit tedious sometimes, but just get over it, okay? Intensive and extensive properties. Wow, this chapter just goes on and on and on. An intensive property does not depend on the amount of substance. So there are a lot of things in chemistry where there's pairs. We had homogeneous and heterogeneous. We had compounds and mixtures. We've got all these pairs of things. It's really easy to get them backwards, right? And so you need to have some sort of a memory trigger or an association to help you keep these straight. So when I think of intensive, I think of intrinsic. Oh, I can't spell it, but I think of it. Intrinsic. That's a really awful S. Intrinsic. That has to do with the nature of something, right? An intrinsic quality. An intensive property is the property of that substance, regardless of how much of it there is. So color, melting point, boiling point, density, these are all intensive properties. The density of something does not change with its size because it's the ratio of the mass to the volume. The mass changes, the volume changes. If you've got twice as much galena, you've got twice as much volume, twice as much mass, the density stays the same. Intrinsic or intensive properties can be used to identify substances. The other side is extensive. Extensive, think external. It's something on the outside. An extensive property depends on the amount. So volume, length, mass, those qualities, those properties are going to change depending on how much substance you have. So intensive versus extensive properties.